Today we're going to take a break from talking about analytical methods to solve differential equations, and we're going to talk about what we can do when those methods fail, because they will. So when you have a differential equation that none of our analytical methods are working for, you can employ what's called a numerical method. There are many different numerical methods available to you, and you've in fact already encountered one. So if we think about a derivative is the slope of a tangent line. It's the instantaneous rate of change. So it gives us the slope of the tangent line at a specific point on a function. So I can use that slope that I can find and the point that it's the tangent line for, and I can find the equation of the tangent line. Now that tangent line is a good approximation of the function for some interval around that point that I used to approximate the tangent line. So if I take that and then I do that again at a different point, and then at another point, and then at another point, and I continue this process, what I'm going to do is have a bunch of little line segments of tangent lines pieced together that's going to give me a pretty good idea of what my solution function looks like. Now, you've seen this. We did this. It was a slope field. We drew a slope field, and then you could pick a point and you could sketch the curve that goes through that point using these pieces of slopes of tangent lines that we put together through those points. So today we're going to talk about another numerical method that is going to be kind of a computational way of doing exactly that. We're going to talk about Euler's method. There are many, many numerical methods available, and Euler's method is perhaps the simplest one to wrap your mind around to begin with. Euler's method is the procedure of using successive tangent lines to approximate a solution to a differential equation. It uses an equation that's a recursive equation where I know that the y sub n plus 1 value can be determined by taking the y sub n term plus h times my function evaluated at x sub n and y sub n. Now n is the number of steps that I've taken. So my initial value, the n value is 0, and with every step that I take beyond that, n will increase. And h is the step size. So whenever we're doing Euler's method, you're going to be given an h value or a step size value. Those are the same thing. And you need to be given an initial condition, an initial value to start from. And after you have those two things, then you're ready to use Euler's method. Now, whenever you do a numerical method, you are approximating the actual solution. So there's going to be some amount of error involved. To communicate that, we talk about something called absolute error. That's when we take the actual value, if we know it, and subtract the approximation. Now we can only talk about error if we actually know the actual value of the differential equation. So again, absolute error is the absolute value of the actual value minus the approximation. And we then get to talk about relative error. Relative error is simply the absolute error divided by the absolute value of the actual value. And sometimes we would like that given as a percent, so we multiply it times 100% to give us the percentage relative error. So let's take a look at an example. I'm going to consider the initial value problem, y prime equals 0.1 times the square root of y plus 0.4 x squared. Y of 2 equals 4. So we're going to use Euler's method to obtain an approximation of y of 2.5 using a step size of 0.1. Whenever you use Euler's method, it's helpful to develop a table. So your table should have all of the x values that you're going to work through. Those x values should start with the initial value. In this case, my initial x value was 2. And they should work up by increments of the step size given, so in this case 0.1, until they get to the x value that we're looking for a value to our function at. So I have x values of 2.0, 2.1, 2.2, 2.3, 2.4, and 2.5 that I'm going to be working from. So let's start filling in our y sub n values for these x values using Euler's method. So y sub 0, which will occur when x sub n is 2, is 4. So I'm given my starting point of 4 for y. Now, to find y sub 1 when x is 2.1, I'm going to use the Euler's method formula. So it tells me to find y sub 1, this is going to equal y sub 0 plus h times f of x sub 0, y sub 0. So I can plug in the values that I know here. So y sub 0 was 4, h is 0.1, and then I have f of x sub 0, y sub 0. And that is of course going to be 0.1 times the square root of y sub 0 plus 0.4 times x sub 0 squared. So I'll plug in x sub 0 and y sub 0. So I get 4 plus 0.1 times 0.1 square root of 4 plus 0.4 times 2 squared. And when I do all of this multiplication and addition, I get a y1 value of 4.18. So I should plug 4.18 into my table in the y1 slot. So now I know y1, and I'm ready to calculate what y2 would be. So again, using Euler's method, I know that y sub 2 will equal y sub 1 plus h times f of x sub 1, y sub 1. So now I'm going to repeat the same process that I had before, except for instead of substituting in 2 for x and 4 for y, I'll put in 2.1 for x and 4.18 for y. And when I do this, I'll find that y2 equals 4.3768. And I should now put this into my table, into the y2 slot. And now that I've done that, I'm ready to find y3. Similarly, it'll be the same process, just using x2 and y2 instead of x1 and y1. And I'm going to go on now and fill in the rest of those y values for us to work with. So there I have all of my approximation of y values using Euler's method. If I wanted to, I could plot these points on a graph, and I could sketch the curve through them, and that would be an approximation of what the solution curve would look like between x equals 2.0 and x equals 2.5. So my estimate, my approximation of y of 2.5 is going to be 5.0768. Now that we have our approximation, it would be good for us to go on to try and find out what our absolute error and percent relative error are. However, we can't actually do that in this case because we don't know actual values for y for each of these values because we don't have an analytical way to solve the differential equation y prime equals 0.1 square root of y plus 0.4 x squared. So we have to be satisfied with our approximation. If we did have a way of solving this analytically, then we would plug in our x values to find our y values, to have a list of actual values. And then we would take the absolute value of the difference between the actual values and the y sub n values that we used Euler's method to obtain, and that would give us our absolute error. And if we simply divided that by the absolute value of the actual value and multiplied by 100%, we would have the percent relative error. It's very common when we use a numerical technique for us to investigate the error involved with it when we can determine actual values. However, there will be times when we can't determine actual values, so we can't investigate the error. As I said before, there are many numerical methods out there. Euler's method is incredibly simple, and because of that, it's a great first one to learn. However, with its simplicity comes a decent amount of error. And so it's not the most commonly used method when we're performing serious calculations. There are other options out there that are more accurate. We'll be talking about the fourth order Runge-Kutta method, which is shortened to the RK4 method in the future. And that method is one of the more accurate options that is used more frequently. So you have that to look forward to as we move forward through this differential equations material.